Today's topic is on nuclear power on one hand, and on this coronavirus epidemic. So what has nuclear engineering to do with the coronavirus mitigation? Clearly, the link is air sanitization. Now, for the coronavirus to spread, actually it's kind of transmitted through air. There is some sort of a confusion over some of these terminologies, whether the virus is actually airborne. Now, in the medical circle, when they classify a virus being airborne, it's really serious. That means it can travel long distance and it can stay in the air for many, many hours. Now, for coronavirus, there are some recent studies indicating that the virus can survive in air for something like 8 hours, and it can actually travel some distance within a room. And of course, the main path, most people believe, is through the direct expiration of some vapors when people sneeze and so on. But since the virus can either attach to tiny particles in air and so on, it can actually suspend in the air for a few hours. And so in some sense, it can still be transmitted through air, but may not be labeled as airborne as serious as something like the measles. So when we talk about droplet is usually quite large, and whereas aerosol is the tiny droplets. It's tiny enough because when you need to have those particles suspended in air, it can't be too big. Otherwise, it is heavy and it can settle down to the ground, to the floor, quite quickly. So when the particle becomes smaller and smaller, and the vapor becomes smaller and smaller into the aerosol scale, then it can actually float and suspend in air and spread. Okay. Okay, let's start with some brief introduction on nuclear power. I'm sure some of you are quite familiar with this topic already. Now, what is nuclear energy? Now, when we burn something like coal or gas, we involve chemical energy, release the chemical energy and use it for, let's say, heating purposes and so on. One way to represent this release of energy is look at the bonding energy of the atoms. Now, for nuclear energy, this would involve the change from one form of nucleus to another, and in the process, releasing energy. Again, of course, this can be represented by the bonding energy of the nucleons. Now, for nuclear power, there are two main kinds of nuclear process to release energy. One is the nuclear fission, the splitting of an atom. Another is the nuclear fusion. Now, if you look at this diagram on the binding energy against the mass, as you can see that around the iron element, it has the most stable kind of bonding energy, in the sense that when at the high atomic numbers atoms, when they split, they can release energy and move towards iron. Whereas the light atoms, like deuterium, tritium, when they fuse to form heavier atoms, then they can release energy in the process, and that is the fusion. Now let's look at the energy release, comparing the fission, fusion to what we can conventionally using the fossil fuel. Now, if you burned or split 1 kilogram of uranium, you can release energy in the order of million kilowatt hours, 23 times 10 to the 6. Whereas the DT fusion reaction to change the tritium into the helium, you can release something like 120 million kilowatt hours. That is quite a bit more than a normal fission reactions. When you further compare this to, let's say, conventional coal-fired power stations, and simply by burning 1 kilogram of coal, you can only release something like 10 kilowatt hours energy. So you can see the major differences in terms of the potential in releasing energy. And that's one of the reasons why nuclear power is a good option to eliminate this greenhouse gases release problem. Basically, all existing nuclear power plants are based on nuclear fission. The ones near to us, like in Daya Bay, and that one is based on what we call the PWR, pressurized water reactor. There are quite a few number of different reactor designs, basically with variations in how fission reactions is managed. In other words, that's, in essence, that's related to how, in the process, neutrons are moderated into sort of thermal energy level so that it can be more efficient in inducing the fission reaction. And also, the differences is in how heat is extracted from the reactor core, from the fossil fuel, from the fission fuel. Like some may use water, some other may use gas like carbon dioxide gas and so on. But the PWR are quite mature technology by now. It's been used quite a bit all the world, even from submarine to nuclear carriers and to many of the power plants. Even though the technology is mature, there are still quite a bit of challenges. And to start with, there's still safety issue because the existing power plant mostly are what we call the second generation design. Inherently, we still need to maintain the cooling of the core after the reactor has been shut down. And without proper cooling, then the core could be overheat and leading to a number of problems, just like the Fukushima accident some years back. But in the newer generations, what we call the generation 3 and the generation 4 reactors, this should be largely mitigated because the design will call for cooling using non-active means that you don't, even without power, there should still be capability of cooling the system, cooling the reactor core. The other challenges is on sustainability. Now, if we use mostly the uranium as a fuel, and we may be able to use thorium and so on in the future, now the actual reserve for this kind of fuel won't provide us with a very long-term solution. If we don't recycle them in some way, we're talking about only something like a few hundred years. Now, if we can use this, what's left over, the spent fuel, and extract some of the leftover elements, we can put it back into the reactor and still use them. In that way, we can extend the availability of the fuel. And that, in principle, could provide us enough energy for maybe 2,000 or 3,000 years. And the third challenge is on waste management. I mentioned already, after the reaction, there are spent fuel. And many of them, those radioactive elements, have a very long half-life. We're talking about hundreds and thousands years long. But if we can adopt the generation 4 reactor to recycle these highly radioactive, long half-life elements and use it as a fuel to burn them, then the amount of radioactive waste left would be much smaller and would be easier to handle. Now there comes fusion. Why we look at fusion? Now, fusion has a number of advantages. We'll talk about it later. But first, let me introduce what fusion is about. Now, as compared to fission, where we split to uranium typically, nuclear fusion would involve the amalgamations of two nuclei, like deuterium, tritium. These are the heavier isotopes of the hydrogens. Now, for the nuclear reaction to take place, basically we need to have these two nuclei come very close to each other. Now, as we all know, the nuclei actually carry some positive charge on them. So if you have two positive charged nuclei coming very close together, you have a very strong Coulomb force, some repelling force forcing them to go away. So we need some means to overcome this strong Coulomb force. So what can we do? Now, actually there are three different approaches we can induce fusion reactions. To start with, we can make use of gravity. This is exactly what's happening on the sun. The gravity attracts the mass, they all collapse inside. That compression will actually force the nuclear reactions. Now, it's quite interesting. If not because the fusion reaction taking place on the sun will actually collapse very quickly. It's because the particle got heated along the way when it's compressed, and the nuclear fusion reaction taking place, that extra energy forces the sun to expand. It's actually the balance of the gravity and this fusion reaction force, this kind of expansion force, that balance the sun in this steady state. Another way we can force the nuclei together is to make use inertia. And this is related to what we call the laser fusion development. We can use very powerful laser beam and compressing the fuel pellet and forcing the nuclei together, and hence to induce the fusion reactions. And then the third approach is to make use of magnetic field. Since when the fusion reaction needs to take place, the gas needs to be heated to a very high temperature. Now, at that condition, basically the gas are all ionized. Basically, almost all the electrons will have already stripped away from the atom. So leaving only the negative charged electrons and the positively charged ions. Now, since these are charged particles, their movement, their motions, actually will be bounded by magnetic field line. They will be circulating on the magnetic field. So by using a magnetic field as a confining mechanism, you can hold those nuclei together and let the fusion reaction to take place. Now, in order for a fusion reactor to generate enough energy, there are a couple conditions we need to meet. We'll start off, we mentioned already, it has to be at high enough temperature. It's hot enough that we can force the nuclei to collide, two nuclei to collide together, and to induce the fusion reactions. We also need them to be in sufficient quantity. That's related to the density. Otherwise, the reaction will be so rare and it will be difficult to achieve a sustainable chain reaction. And then the third condition is on so-called confinement. We need to be able to confine the particle within this reaction chamber for sufficiently long time. Otherwise, the particle will be lost, energy will be lost, and we can't sustain the fission the fusion reaction. So if you look at this diagram on your left hand side, the lower corner, the y-axis is related to this what we call the triple product. That is the product of the density, of the energy confinement time, and also on the temperature. And the x-axis actually refers to the energy of the plasma, the gases. And if you look at the bounded area, right to almost the right-hand top is the condition we need to achieve the new fusion reaction in a proper fusion reactor. So over the years, we have started basically from the left-hand down lower corner, move from the first early tokamak, T3, move all the way to recent years. We've seen a lot of data points on this line and bounding towards something we call ITER. Now, ITER is an international collaboration experiment on nuclear fusion. It's being built, I think it's almost done, at Cadarache in France. So there are 7 major parties involved in it, of course, involving like Europe, EC, the US, and China, and so on. That is the one that's going to hopefully give us the chain reaction conditions. So similar to the condition necessary for the next stage to build a demo reactor. Now let's take a look at how fusion development took place over these years. Now, the first application of nuclear energy was kind of unfortunate basically in the making of bombs. We have the first fission, the splitting of uranium, fission bomb actually used plutonium in the bomb. And that was developed during the Second World War in the 40s. And then about a decade afterward, we see the fusion bomb in the 1950s. By about 1958, fusion research actually was declassified. It all took place very interestingly because out there in South America, Argentina claimed they have actually developed a fusion reactor. Of course, that turned out to be not quite true, but that event actually triggered much more rapid development in nuclear fusion all over the world. And the work on nuclear fusion at that point was declassified, so it's not just within the military circle. So the whole civilian R&D on fusion power really started. So you can see on the top, the right side, you can see something like a torus. This old picture. This is on a tokamak. It's labeled as a T3 tokamak. It was built in the Kurtchev Institute in Soviet. It was at that time actually one of the first design of a magnetic confinement that gave a very promising result. Even so, it is actually, if you look at the diagram, I reproduce it here on the right lower hand side, the T3 as it's at the very low left hand corner in the diagram. But that result actually also surprised the world, and scientists from the US, from UK actually were sent over there to verify the results, and they all see that they were able to achieve the first high temperature plasma. And that's back in the 1968. At that time, scientists were very excited, and they all thought that in about 15 years, we will have fusion power. And over the years, many developments, mainly what they found was that despite different kind of magnetic configuration to confine it, Tokamak is only one of them. We have other type, like stellarator, like reverse field pinch, and so on. But Tokamak by far is already the most promising. Even so, there's still what we call instabilities ruining the confinement time. We're still losing particles, losing energy. We can't confine them long enough to achieve a sustained reaction. But there are a number of major breakthroughs. And by about the late 1980s, we were able to overcome the global instability and so on, and still left with some finer scale ones. So the scientists began to be more hopeful, and they would say, well, fusion should be 25 years away, not 15 anymore. By the late 1990s and early 2000, that Mendel's experiment is already has been able to demonstrate fusion reaction in a controlled manner. We have already demonstrated the powerful, the extra high energy level of the fusion reaction in a ball. But in order to harness the energy, we need to be able to do it in a controlled manner. And that's why we have all this development work. And by the late 1990s, there were a number of experiments that we were able to achieve that. And so the international effort now has been put together on this ITER, this demonstration, one of the main research reactor for this current stage to study the engineering problem, to address some of the engineering issues. Now, let's look at some of the demand over the time. I mentioned already, by the late 1990s, we have already been able to demonstrate controlled fusion reaction within a number of devices with the name like the JT60 and the JET. In JET, that's back in 1997, they actually have to inject something like 24 megawatt into it, but then they only got 16 megawatt out of the fusion reaction. So we still can't reach the break-even point yet. So we need to still put more energy into it than we can harness. But at least it is doable. It's already demonstrated what we call the engineering, the scientific feasibility. So the next stage is to demonstrate the engineering feasibility. This is why the world needs to build the ITER machine. The ITER machine mainly is to address a couple of engineering issues now, like how to maintain the reaction of this so-called discharge. We actually ignite the plasma and last it for some time. But so far it's actually operating in a pulsed mode. We would like to extend this even in the form of pulse, but we're talking about minutes rather than tens of minutes rather than seconds and minutes. Another is that because the plasma is at such a high temperature, any small instability would allow some of those particles to leave, and then they will have a chance to touch the confinement physical wall. Because of the high temperature, they can actually melt through the wall and create damage. So one of the main areas in the ITER study is to see how they can control this kind of instability issues, make sure that this high temperature plasma will not damage we call the first wall. And when all this has shed our light on how to build a reactor, then we may be able to move on to the next phase. So that will become a demo. But that won't be around us for another something like 30 to 40 years. By the time we have some real result coming out of it, it'll probably be 40, 50 years away from now. And you can see the scale actually getting bigger and bigger. For JET, we're talking about volume about 80 meter cube. And for ITER, it grew to 800 meter cube in volume. And the forecast for the demo will be reaching something like 1,000 to over 3,000 meter cube. And that is quite big. There are also concerted efforts right now at different laboratories in the world trying to come up with a slightly different magnetic configuration, perhaps to reduce the size of it. So why are we so interested in the fusion power? There are quite a few advantages. To start with, the field that we need for the fusion reaction, we rely on things like deuterium and lithium. In essence, we got quite a bit of them on Earth that we can extract. They estimated if fusion become possible, we can actually extract the energy from these fusion reactions. We will have enough this kind of field to last for something like millions of years. And another advantage is that it doesn't have many of those radioactive waste. During the fission reaction, actually it's slightly radioactive, but not with the waste. So without large quantity of waste, it makes it much easier to handle. And also it's inherently safe. If there's any accident, any damage to the reactor, basically you just stop the fusion reaction. And the amount of radiation that can, radioactive material that can come out of the reactor is pretty small because they're all in gaseous state, and deuterium and tritium are not that damaging. So again, we don't need to recycle this, so that's again where we need to so-called proliferation kind of concern.